Let me find it here because I wanted to give everybody credit for one of the problems because it was confusing. So let's first just look at the problem. I sent you a note about it, but I think it might help to have it explained more. So here we go, and it's a homework assignment, and here's your homework for Wednesday night. It's due, this is due Wednesday at midnight, and it's pretty easy, very straightforward. It's just we're going to cover this today. You could do this by the end of the class, but let's look at the homework that was due last night. These confounder problems, they're kind of confusing. So this was the problem that, let's read this. It said the New York Times published a front page story with the headlines, "Study finds no sign that testing, study finds, where am I? No sign that testing deters drug use." So this was a real study where drug testing was implemented in, with 76,000 students. So the study reported results from a study of 76,000 students in many high schools and middle schools nationwide, comparing reported drug use in those schools that had decided to implement a drug policy to those that had not. So this is giant sample sizes. Now, in each school, students filled out an anonymous questionnaires asking them whether or not they used drugs. And this was at the end of the study, after they'd already implemented the drug testing or hadn't at the end. The study found no difference in drug use rate in schools that tested for drugs compared to schools that did not. So they said this program of testing for drugs doesn't help. It doesn't reduce the drug use. Okay, so but it was an observational study, and it suggests that drug testing is not effective, but it certainly hasn't proved it because we don't have a randomized study. So then I said, which of the following could confound or mix up the results? All right, so now, what is a confounder? You have to remember that a confounder is a difference. First of all, confounders only happen in non-random studies, and all observational studies have to be non-random, right? So the problem is that there's a difference between the treatment and the control groups. In this case, the treatment is drug testing, and the control group is not drug testing. So there's bound to be difference at the very start of the study, before they start drug testing, right? The schools that decide to sign on to this program are going to be different in many ways than the schools who decide they don't need this program. One big difference might be the initial, right here, might be the different initial rates of drug use. The schools who chose to implement the drug testing may have a higher rate before testing. So if they didn't measure that, which they did not, look at that before, ahead of time, then the fact that they're even at the end could mask, doesn't tell you anything. If they're even at the end and the school that implemented the drug testing was higher to begin with, well, then the drug testing program did work, right? We can't tell because they didn't look at that difference. That could confound something. It's a difference between the two groups that is not a result of the drug testing, but happens before. Remember, confounder is a difference between the treatment and the control group, a systematic difference other than the treatment. It was established as a difference that occurs before the treatment that could be a possible cause of the result. So that for sure is yes. Now, lying. This was a hard one. I said, let's think about it. Students at schools that test for drugs may be more apt to lie about their drug use, even on anonymous questionnaires. Now, why it was confusing is because I didn't tell you whether this difference between the schools that test for drugs and the schools that don't, this difference of lying, they have a higher rate of lying, happened before the drug testing was implemented or afterwards. If it happened before, if it was just, let's draw a picture. So I want to go back to the document camera so we can draw a picture of this. So let's think about this. And let's go to the document camera. All right. So the question is this. Remember, does the lying cause, let's say the difference happened before. Let's say it looked like this, all right? We think lying is a confounder that leads both to the treatment and the response. Now, the treatment was the drug testing, and the response is what? Higher, it's a little bit confused because it's higher reported drug use. So this measure is very connected with lying. And it might not be a good measurement of what they want to, they really want to measure higher drug use, not higher reported. So that's not a good measurement to begin with. So there's another problem. But let's say the schools that did the lying cause the drug testing? No, it didn't cause the drug testing. Did the drug testing cause the lying? Well, it might have if because there were, it could if there was no difference beforehand in the lying, but the drug testing, because there is that drug testing, people get scared and it causes them to lie more. Well, that would be kind of a causal link and not a confounder, right? Do you understand? If the drug testing actually caused people, and it could, because if your school is testing for drugs, you might be worried about it. You might see the consequences of those people who get caught for drugs. You might think that this is very serious and get scared, and then it would cause more lying, in which case that would be a causal link and not a confounder, right? Do you understand? But what if something else, lying, was just, the schools, there's some kind of culture that schools that drug test, you know, they have more, they're going to choose to drug test because the kids are both drug users and more likely to lie. So it looks like this. With no real, these are connected, but they're both coming from elsewhere. So this is not causing this. This could be a confounder because lying also leads to a higher reported drug use. So it's a very complicated situation, but this is a confounder because it's a difference that occurred. A difference that occurred between the schools that drug test and the schools that don't, not as a result of the drug testing, but beforehand. Does that make sense? Does that make sense? This, by the way, is very complicated. These causal patterns are something that's sort of on the cutting edge of statistical research right now, trying to tease these out. And so it's become much more sophisticated, and this use of these arrows are becoming more and more important. So if you look on Wikipedia, you can look more about this. You can learn more about this. But that's why it was very complicated to give you as a beginning example. And I didn't specify which one it was. So I just wanted to clarify that. All right, so now, remember where we left off on page 19 here. And as you recall, we had looked at our own survey data, and we can just quickly look at it again, just for fun. And what we're trying to do here is we're looking at how to remove confounders from correlations. So in our own bonus survey, we go to the data program. We're going to choose our, now the other one's up too. We have two of them now. Stat 200, here's survey 1, and you can look at survey 2 results as well. We are going to be exploring this with our bonus problem that's coming up real soon, and we're going to look at this one now. So we're looking at scatter plots here. So we're going to scatter plots, and we said, okay, we wanted to look at the correlation on between shoe size how big your foot is as a predictor of how many pairs of shoes you own. And we saw that there's this negative correlation here, negative 0.2526. And we said, okay, does this mean, if you look on page 19, you have a similar data set from before, does it mean that the bigger your foot, that somehow that causes you to have to buy fewer shoes? Or is it some confounder? And people said some other thing, some other difference between big feet and little feet, right? People have big feet and people have little feet. The treatment is either the bigger feet or the little feet. Treatment and control, we're comparing those two groups, and we see this does it cause people to buy less shoes? Or is there something else that's a cause of both of them? And then people said gender. They said that because females have smaller feet and have more shoes, and males have bigger feet and less shoes, and that's what's driving it. So what we did, and if you want to do this yourself, you can split on anything you want, any variable you want. You can do multiple splits with multiple categories. It's really fun to play around with this, but I have it right here at gender, so you just click split plots, and then you see that correlation goes away completely. And we get two regression equations here where the slope is basically 0. So it says the number of pairs of shoes for the guys is some intercept, which is about the average, plus hardly any, the average for guys, the average number of shoes, and not much effect at all for the shoe size, a tiny little bit and a tiny little bit there, negative both. And you can see the female intercept is much bigger because they have a bigger average. It's not exactly the intercept because this isn't exactly 0. We'll explore that more later, but what I'm talking about right here is that the average pairs of shoes for guys is 6.621. That's not exactly this because you're subtracting off a little bit here. And for this one, it's not exactly 12.74. If it was an exact slope of 0, it would be. You just predict the average. All right, so, but essentially, within random variation, there's no correlation. All right, so let's explore this in the, let's go back to our document camera on page 19. All right, so, first of all, this is really hard to read, and I'm sorry I didn't post your own data. It would have been more fun, but I had to write this book ahead of time, so I used some old data set from a former class. All right, so what do we have here? On this axis, on the y-axis, we have the number of shoes, number of pairs of shoes, and it runs from, here it says 0, 20, 40, 60, 80 to 100. Okay, and then on the x-axis here we have your shoe size. And here we have 0, 5, 10, and 15. So there's a few people with 15 and somebody with a size 4, it looks like, but most people are more in the middle. So the question was, and here we have our correlation coefficient. This time, this data set, it was much stronger. Now, so the question is, does the treatment cause the response? And we can basically, is larger feet, do larger feet cause less shoes? You could have just as well said smaller feet cause more shoes. Or is there some confounder, like gender? You could say, in this case, I'll say males cause both the larger feet and less shoes. Or you could say females cause both the smaller feet and more shoes. All right? To find the confounders, let's just do it the way we've always been doing it. You list the differences between those with big feet and those with small feet besides the treatment, before the treatment, all right? Besides that, that could be the underlying reason why people with big feet have fewer shoes. So here we'll call this the treatment group. And this is the control group, which just means a comparison group. And obviously, we can't turn this into a randomized experiment. We can't randomly assign people to have either bigger or smaller feet. So this has to be an observational study. Now we said, okay, we thought gender could be a confounder. Why? People with big feet, what's a difference between these two groups? Right? A difference that happened before their feet got big and small. Not something caused by having big or small feet, but something that happened is a difference already. And that is that more males tend to have big feet and females tend to have smaller feet. So there's a systematic difference between these two groups, right? That also, because we know that males aren't as interested in buying shoes in this culture as females, that could cause the result. So is that clear? It's something that happened before. It's not like, oh, you have big feet. Well, now with gender operations where you can switch your gender, you could say, well, like for me, I have these giant feet. That makes me more likely. I feel maybe more masculine. Maybe I'd be more likely to then. Big feet could cause me to change to a male, which would cause me to then buy less shoes. But that's a little bit far-fetched in this case. Okay? Do you understand? But that would then be the causal link, because that would happen afterwards. But in this class, we're looking at people who were assigned one of these before by some random fastest sperm that just won out the race in a random way, and then the males led to larger feet. And through some cultural causation here, probably, because it's not true in every culture, but in ours, to less shoes. Do you understand? Yes? What? Wealth. Could wealth be? People with bigger feet would be wealthier. They might be. I don't know if that's true. If people with bigger feet would be wealthier, but then they'd also then buy less shoes because they're wealthier. I have so much money, I don't have to show off my feet. I can just have a giant car to drive or something. Is that? I'm not sure. Yeah, it's kind of far-fetched. Yes?
Gender better than male?
Yes, gender is better than males. I just want to say a specific case. It's just because I wrote the larger feet and the less shoes. Males versus females. Yes, gender is more than gender, because you could easily write it as size of foot, and yeah. It's more general, yeah. Any other questions? Okay, now, so what do we do here? Well, you saw what we did. We stratified along this confounding factor of gender. So let's just get a visual, an intuitive picture of what we just did with the data program. We say, how can we determine whether it's the size of one's feet or the possible confounder, or maybe some combination of both, that's the underlying cause of the number of shoes? Okay? So, what do? We stratify the population into subgroups where the confounding factor is the same. So we look at males and females separately. That's what we did. We split those graphs. So it can't be males because both groups we're comparing, big feet to small feet, and everyone's a male. So if we see any difference, it can't be that. All right? So this is what we did. So we looked at we had the small feet here. Okay, so first of all, we're saying what? That in terms of the number of shoes, that's what our response variable is. People with small feet have more shoes than people with big feet. But they're also more likely to be female. So how can you tell whether it's the female or the size of the feet? You can't. That's our problem. These are small feet, but they have many more females here, and females tend. So we want to break it into two groups and look at them separately along our confounding factor. So let's just look at males separately and females separately. Now, males vary. Some of them have small feet, and some of them have big feet. And this is just but if it was due to the size of the feet, we'd still see this, here. This is the axis that I'm looking at. This is the response, the number of shoes. Okay. Now with males, I did an exaggerated version here. Everyone has fewer shoes. Everyone does. But the question is there a difference? There still could be an effect. There could be the reverse effect. It could be that bigger feet are just like, I don't know, it doesn't have to balance out like this. It could have a different effect for males and females. But in this case, as we saw, it completely disappeared. And same here. I mean, there was still a slight negative in both directions. If you had given the same survey back when I was in college, I bet there would be quite a big negative here, because smaller feet were what I call the Cinderella effect. Having a big foot, I was very aware of this, that stores didn't carry, they didn't think they were pretty big feet with women, and so I didn't want to show off my feet, so I tried to hide them. I certainly hated going to shoe stores because every time, why are your feet so big? I got a lot of negative feedback. And so then, and girls who had very small feet wanted to show them off everywhere and had a lot of shoes. I mean, this was true in my high school. So it would have been like the Cinderella effect, and that wouldn't have been apparent for men. That would be an interaction effect. But they both disappeared. And so what do we conclude? We conclude clearly it's not the size of one's foot that's causing this. It's whether you're male or female that's causing the result we see. All right? So now there's two ways to control for these confounders. Control is used in so many different ways in statistics. We've already seen control as a comparison group. Now, two ways to control to get rid of the confounders, right? One is stratification, which we just did. Just break into two separate groups completely. And you saw that. That's exactly what we did. And we got two separate regression equations, two separate correlations, one for males and one for females. And that gave us the most information, a lot of information. Another thing we can do, though, is called modeling. And we're going to be doing a lot of that. And that is, instead of having two separate regression equations like we just saw, we'll have one regression equation with two variables. One of them, so we'll say the number of pairs of shoes will be predicted by two variables. One, how big your foot is, and the other, whether you're male or female, a binary variable, whether you're male or female. And we'll see how that's another way to get at this. But if there was any difference between the two slopes, that would show up in stratification. We'd see it, but it wouldn't in modeling unless we added another third term called an interaction, saying if you're male, there's one slope, and if there's female, there's a different relationship. We'll get to that later. So we're going to be doing that. In part 4, we're going to look at the same exact example, both as stratification, which we've just done, and by multiple regression with with two variables. So we'll do that in part 4, and so you'll get a feel for what's going on. Okay? So observational studies are likely to have confounders. Randomized ones don't, because the treatment and control group are balanced to begin with. I can't stress that enough. They're balanced to begin with before the two groups, before you ever even look at the treatment, they're balanced. Sure, they're somewhat different, but they're not systematically different. With the big enough sample sizes, all the differences you see between the two groups, if they're randomly assigned on all variables, not just the ones you can identify as might be important in influencing the response, but on all variables, just by the law of averages, are going to be very similar. And the differences you see are going to be due to the randomization. There'll be slight differences that we can measure with a probability model. That's exactly what we do with p-values. We measure those the likelihood. You're going to have some differences, but then when we see in the response a difference beyond what you'd expect just by sheer chance variation, you say, okay, what's the likelihood of that happening? Just by randomization, when the null is true, when the treatment's not doing anything, and if the difference is so big and it's so unlikely to happen by just accidental difference, random differences, then we say that's the p-value, and if it's small enough, we reject that null and say there's a particular cause. That's why we can prove causation. There's some cause for it. We can't say which particular cause maybe, but we know there's some cause. And if we singled it out, then we can say that's the cause. Does that make sense? So that's the point. All right. And thank you for a few students, one in particular I see right here, who pointed out helped me get more thinking about this more, because it made me realize that lying example was confusing and lying could easily be a causal link. So thanks for that. I love it when you help me out that way. Just makes my teaching better. All right, so now we've talked about this a lot. Prediction versus causation. This is a big theme for this course. Now these from here, chapter 6 and 7, they're very short, and I want you to carefully read them on your own. You'll get a lot more out of it if you do, but I just want to go over the basics with you now. As we've said many times, we look at data to do one or both of two very different things. The prediction, we want to know what to expect. Diagnosis, prognosis, we want to know all that. With medicine, for sure, you want to know how to predict whether you're going to get some disease here. In finance, you want to predict what your future income will be, even if you can't change it, just so you know what to expect and how to adjust your spending. Very important. But what is finding causes then? We want to know not only what to expect, but how we might be what things can be changed to change those expectations, right? So in treatment, you want to know what you can do to change that. And it could be, same with your wealth, right? And what you might do to change that might have the opposite correlation. For example, if you have some cancer diagnosis and you get radiation treatment, well, that is negatively correlated with health. Because people who get radiation are sick, a sick population, right? But you still want to do that. And same with here, a classic example for an action you might take to save money would be to not buy a car, right? Even though car ownership is positively correlated with wealth. I mean, particularly like Rolls-Royce, right? People who have a Rolls-Royce and super fancy cars, very expensive cars, well, that's correlated with high incomes. But if you want to increase your wealth, don't go out and buy a Rolls-Royce, because that's the opposite. You'll go broke, right? You don't want to buy a Rolls-Royce. So that's pretty obvious, right? Okay. Why I'm stressing this? It's obvious when we know what we're talking about. It's not obvious when you try to just do statistics without thinking about your data and doing it, then all this stuff that's so obvious to us isn't. So you have to know the data, is what I'm saying. You have to have some understanding of it. Okay, so this is correlations, not causation. That's what I'm saying here all along. And you might want to know, well, consider health and wealth. Certainly they're associated. Healthy people are wealthier on the average and vice versa. That's enough to make a more accurate guess about someone's health if you know their wealth and vice versa. That's what regression will show you. But it doesn't tell you how much you can change someone's health by giving them money, or change someone's wealth by getting them healthier. So what causes what? That's what we're interested in. Does health cause wealth? Yeah, it might. Does wealth cause health? Or does some other factor, such as understanding statistics, that's what this is, cause both of them? I would hope so. I believe so. I believe it would make you both. You understand stuff better financially and medically. Those are the two areas I like to think about. And yeah, statistics definitely helps you with both of those. But it's all, and then we'd call understanding a confounder here if that was the case. But basically, it's much more complicated than this, and probably all of them can be going on, right? So you need other types of data to decide that question, right? So in the absence of a randomized, first you want to think, can you do a randomized experiment to get at this? Could you? Could you randomly, because then you could get it. Could you just randomly assign people to be healthy or sick and see what happens to their income, or randomly assign people to be rich or poor and see what happens to their health? Could you? Well, it doesn't seem likely that we could do that. So when it seems it's hard to do that. So in the absence of that, the next best thing, remember, randomized experiments are the ideal we're looking for. So in the absence of that, what I think everybody should always do, and some brilliant experiments have been done this way, is by seeing if there's such a thing as a natural experiment that mimics randomized experiments, okay? A natural experiment that could be used to check any of the above. Can you think of any non-confounded random change in wealth? What I mean by non-confounded, just somebody randomly getting assigned wealth, and there's no differences between that group that randomly get assigned it and the other group at the start of the experiment that could be used to check if wealth causes health. Can you think of any way that, yeah?
Like a lottery?
Yeah, the lottery's a perfect example. I don't know if enough work has been done on this, but I think it would be really fascinating. You would compare everybody who participates in the lottery. There's mostly losers, but then there's going to be a collection of winners. So they get really rich. How much does their health improve compared to the other people who play the lottery who always lose, who've never won? I think that would be a very interesting question. You'd think it would, because they get wealthier, but does it? It's not clear. That's a great randomized experiment. So lottery winners, that's a great idea. Randomly get wealthy. Compared to and you compare them to lottery losers, not just to the general population, but to the other people playing the lottery. And then, does their health improve? I would like to see an experiment like that. I think it would be a great idea. This, I think, is harder. Anyone that could be used to check if health, a random change in your health, really changes your wealth. Yeah?
If you chose people from similar original backgrounds, maybe one of them got like a devastating disease, or even just you measured like how often they got disease, it kind of pushes the line on whether it's observational or like naturally random.
It does, because there could be different. How would you minimize the differences? What he said is what you would do is look at two groups of people who are very, very similar, and then one randomly gets some illness, right? And I think the best way, I'll take it. You really have to have the two groups be very similar, and probably, I think, identical twins. This would happen with identical twins who are raised the same and everything, and then one of them gets some kind of illness. How does that affect their wealth? That might be the closest we could get to it, right? That's what you're getting at. So,
just family members or people in the same neighborhood would be better than nothing, but
yeah, but there's going to be differences there. Yeah, I think the closest we could get would be look at identical twins, where one, gets sick, not because he's doing anything to get sick, but just happens to. They have the same environment. One gets sick. Does the healthier one you look at a whole group of them, do the healthier ones get wealthier? Okay, so now what we're going to do is what we mean by causation, because you're going to see if you've taken statistics and before, and all of you have, and if you go further in statistics, whenever you look at these regression models, this word explain comes up a lot. Explain. And it doesn't really mean cause. It just means that it helps explain that an independent variable is helping, a predictor variable is helping explain some of the variation in your response variable. So, for example, you could say that, like your shoe size, the size of your right foot predicts your height pretty well, right? Or your height predicts the size of your right foot, let's say that. But your left foot would predict it even better, right? Would predict it even better. The size of your left foot's going to be an extraordinary predictor of your right foot. But that doesn't mean it gives the changing anything with your left foot size is going to change anything with your right foot size. It's not a cause, even though it explains it well. Explain is used in statistics in a different way than it's used in ordinary language. In ordinary language, when we say explain, offer an explanation, we think of a causal explanation. I just want to warn you, when people use the word explain in statistics, that's not what they mean. So what do we mean by causation in statistics? Well, there's a very specific meaning for it. And what we mean is if you could change A without directly changing anything else, would that make B more or less probable? So if the two are associated, like right foot size and left foot size are unbelievably strong correlation. But that doesn't mean one causes the other. One explains the other but doesn't cause it, because changing one is not going to do anything to change the other. So now back to our shoe example, and we've seen that among our students, gender is correlated with the number of shoes owned. Females tend to own more. Does that mean that female gender causes people to own more shoes in the definition we're using, or that owning more shoes causes people to become female, or that some unknown factor causes both of them? And so the correlations that we see don't answer that, but independent knowledge, of course, will, because gender is almost always set before shoe ownership. I mean, most always, in most cases, it's set before. So we can absolutely eliminate this, right? You can't say that shoes, how much shoes you have, cause gender, because gender happens first almost always. So this is eliminated because of this right here, right? So it's not that. Now, what about this one? Well, we think that whatever determines biological gender, which is which sperm wins a race, is almost entirely accidental, almost certainly unrelated to anything that would influence your taste in clothes. So yes, it's what determines whether you're male or female has nothing to do with your taste in clothes. There are certainly unknown factors influencing both of them, but they aren't the same factors. That's the whole point. They're not the same factors, so they wouldn't explain why we see these two together. Okay? So that eliminates this. And that leaves this one, right? But it doesn't tell us, so now in our definition, the only difference was, okay, females happens first, and we think that it causes shoes, but that doesn't tell us what sort of causal links are on the path from gender to shoes. There's a huge causal chain here. It doesn't tell us, for example, how much that causal pattern depends on social customs, on culture, which it certainly does. We're just taking, in the data that we have, we're saying that it's a cause because it happens first, and if you change it to male, it changes how many shoes. When you look at males versus females, you get clearly a different result. It's much less probable that they'll have as many shoes, males. So it satisfies our definition. But There's a long, that doesn't mean we know. We don't think it's a genetic thing. We're not saying that at all. There's a long causal path here that's almost certainly culture dependent. So, that is the causation according to our definition, but that doesn't mean we know the causal path. There's a long causal path, so it's clearly different in other cultures. So I'm not saying just because you're born a female, you're going to have more shoes. I'm saying right now, it's in this culture, what the data that we're looking at now. But there's a long causal chain that's certainly culture specific. Or culture dependent. See next page, I go into that. Basically, just think about it this way. You've heard the expression in poor countries of keeping women barefoot and pregnant. No shoes for them. That was for much of history. Men had more shoes than women. So that would mean less shoes for women. It would be a different pattern. Right? Because only rich people and women were kept barefoot and pregnant. You've heard that, right? So then it wouldn't follow the same pattern. It would be a different cultural pattern. And maybe in some cultures there's no difference. But what I'm saying is I'm not specifying what this causation is. I'm just saying that it exists right here in this culture, in our group, in our data. Okay, does that make sense to everybody? All right. So I want you to read that, and on the next page you can read, I went into a big long explanation of that because I think it's interesting, gender and shoe size, how the context matters. And so you can look at all different ways that it might change depending on the situation. Okay, but that's for later, for reading later. Now, and these finding causes is so important that I want everybody to certainly read this summary. All the summaries are important, and the best way to assure that you can deduce causation is through a randomized controlled trial. But when we have observational study, that means it's hard, but it's not impossible. So many people in statistics say, oh, they'll teach you this over and over and over again, and they'll say, okay, it's hard to do. If you have a randomized control, fine. But in everything else, we're not even going to try. But I think it's very important to try. And I think we come to these conclusions anyway. So I think it's as much as we try not to, our minds always look for causes. That's what people are. So it's much better to really try to be clear about it and try to draw causal patterns and think very clearly about what we mean. Otherwise, we're going to slip into saying, oh, we're explaining the data, to very short hop, skip, and jump to saying that that explanation is a causal factor. So we have to be very careful about this, and I think it's really important to think about this. And we are going to be doing that throughout the course. Okay, now, let's see, what's the next page? I think here I just want, people always ask me about, okay, two types of randomization. I'm not sure we talked about this, but whenever you're making these statistical inferences, you're using a random, you have to model whatever situation you're in with a probability model. You have to see what in your situation has random variation. And there's two types of inferences we make. One you can think of as causation. If you see a relationship between A and B, does one cause the other? Okay, does one change that? We talked about that. And this causation, you get at through a randomized experiment. It's how the subjects are assigned. That's how you get the causation, through a randomized experiment. An experiment where you make the assignment, okay? You make an assignment. And then you can conclude, if you do that, if you randomly assign, you can conclude causation. Okay, but there's another type of statistical inference we do, for example, when we do pre-election polls. We're not talking about causation, we're talking about just extrapolating to a larger population. Extrapolation, right? Taking a sample, a random sample from a larger population, and we're using inference and many of the same procedures to say how confident are we that we can predict what the entire population parameter. So if you see a relationship between A and B, would the relationship hold up if you looked at a broader population? So that's another type of statistical. We do both of these, right? And that is how the subjects were chosen. This is sampling. So this is sampling, basically, issues. And these are experiments. Okay, or observational studies. Experiments or studies. And this is sampling. Now, everybody says, okay, how the subjects were chosen. Well, if they were randomly sampled from a larger population, then we can extrapolate. That says extrapolate. You can't, you can only extrapolation only if they weren't assigned. So I just wanted to clarify those two issues. And if they were non-randomly sampled, for example, lots of experiments were done just on who do I mean? I mean the subjects in the experiment weren't taken from a larger population. They were just chosen, and then they were randomly divided. Well, then we can still conclude causation, but we can't extrapolate to a larger population. For example, if it was just done on college sophomores, we can't extrapolate to a much wider population. Or if there's something, but what people do all the time, we can still say there was causation happening in that experiment. Causation only, okay? And then you can do neither if neither of those conditions happen. But people do this very loosely. If subjects are representative cross-section, even though they weren't random of a wider population, people often extrapolate anyways, but you have to be very careful about that, okay? So I just wanted to clarify those two different uses of statistics here, inference. All right, now, here we are we're just today, this is part 3, on simple linear regression. That means you just have one x predicting one y. And I'm sure you're all familiar with the scatter plots. And what we're going to do today is we're just going to do these 3 pages here. And it's pretty much review except for one feature that you might not have seen if you weren't in Stat 100. But here we go with this simple linear regression. And we use a scatter plot. And that's a graph used for showing the relationship between two variables we usually call one x and one y, and the one we assign to be called x is called the independent variable, and we think, well, how does then we think of y as depending on the value of the x variable. So y is the dependent variable. Usually you think of the independent variable as used to predict the other one. So you would be more likely to predict, like if you're predicting your final exam scores from your midterms, rather than vice versa. Now, there's a fun video that I think I'd like to take a little break now. I think we have enough time. It's just a 5-minute video. So let's see if I can just pull it up. On correlation and causation, and it's on YouTube. Okay, so am I on YouTube now? So I'll say it's called Spurious Correlations. It's by this guy, Tyler I think it's Stevens-Vigan. Let's just see if that comes up.
Hey, my name's Tyler Vegan, and I'm here to talk about spurious correlations. You might have seen some of my charts based on a program I wrote to find correlations between completely unrelated sets of data. For example, there's a correlation between the divorce rate in Maine and the per capita consumption of margarine in the United States. And there's a correlation between the number of worldwide non-commercial space launches and the number of sociology doctorates awarded in the United States. But what do those mean? Anyone can plainly tell that there's not actually a connection between margarine and marriage. But everyone considered the hypothesis for a split second and said to themselves, are we launching sociologists into space? And that's the part that's so cool. We were scientists, if only for a moment. We saw data, we formed a hypothesis about that data in the form of a causal mechanism, and then we rejected that hypothesis based on our personal experience with the world. That's a big deal, and it's the part that computers can't do. Research is about discovery, but only humans can actually make discoveries, though computers are a great tool. The purpose of the spurious correlations I show is not to say that data is ambiguous, you can interpret it however you want. No. Statistical data can show correlations, and then it's up to us as rational thinkers to establish whether there's actually a connection between the variables or if it's merely a coincidence. We do this in two ways. First, we need to mathematically prove that a correlation really exists. Scientists have much more sophisticated methods of determining whether two variables really correlate by using p-values and significance. But I am not an expert on statistics or number theory, so I'm not going to talk about that part here. Instead, I'm going to leave that to another YouTuber, like Singing Banana, or Numberphile, or ByHeart, to make a video about it. And when they do, I'll link it here. Second, to establish a connection between two variables, we need to establish the why. The why is usually called the causal mechanism. The causal mechanism is like the verb in a sentence connecting two things together. For example, there's a correlation between how many videos I've watched by SciShow Space and how much I know about space. The causal mechanism is that Hank and Caitlin are teaching me more about space. The teaching is the verb, and it's causing me to know more about space. Finding causal mechanisms is the key goal of a lot of scientific research, because when we find causal mechanisms, we learn that much more about the world around us. Sometimes we see a correlation that we can't explain, and it might inspire us to search for a potential cause. A good example of correlations leading to conclusions is the connection between smoking and lung cancer. In the early 1900s, the incidence of lung cancer was on the rise, and no one really knew why. Then, in 1929, German physician Fritz Lickent published a paper in which he showed that lung cancer patients were particularly likely to have been smokers. That is, there's a correlation between smoking cigarettes and the incidence of lung cancer. That paper led to a lot of research in which we learned about the dangers of smoking, but it never would have happened if someone hadn't seen the correlation and then researched. To sum up, correlations are a great starting place, but it's up to us to be critical of the correlations that we see. Correlations between two variables could be merely coincidence, or they could be the result of an underlying causal link. And every time we see a correlation, we have the marvelous opportunity to try to figure out which one it is. I'm Tyler Vegan. Have a great day.
Okay, so he said something. What he said at the very end was that correlations that you see could either be basically just complete coincidence, accidental almost, like the ones that he showed, or else have a clear causal link. But he didn't really talk about when there's clear confounding or when you have to tease out confounding. So he just looked at the two extremes. I think it was very valuable. He does say that he says how important it is that, for people to really think about what's going on. And that's the part I like there. But so the types of crazy correlations that he showed, these accidental, coincidental correlations, he found by searching databases and cherry picking them. He never would have been able to find that. He looked for some pattern, like here's one from his website that shows the number of people who died by becoming tangled in their bed sheets over, and it's a time-dependent one. And then he just searched through tons and tons of data sets to find one that matched it. Okay, so it's sort of an accident of just having these giant, this isn't something that we'd be wondering about if he hadn't done this cherry picking, looking for this. And he found another correlation, which was the total revenue generated by ski facilities. Why would being tangled in your bed sheets? It's just a crazy correlation. So that's the ones he talked about. And then he talked about the clear causation ones down here, but he left out these two categories where you really have to do some work thinking about what the confounder would be. Well, the clear confounding is one where we don't have to do so much work, but these are associations, real associations we see in life that have clear confounders. So like this lighters causing, you see lighters being associated with lung cancer, and we saw the confounder smoking. These are iconic examples that help you understand clear confounding. We see them for a reason, not just by sort of manufacturing, like finding patterns. These have no reason, really. Okay, so here's another one. The number of deaths by drowning in ice cream sales. Okay, so let's think about that. Certainly people, this is a very classic example that I learned when I was teaching learning statistics. You see this pattern, ice cream sales, and death by drowning. And when ice cream sales goes up, there's more death by drowning. Why? Well, this is when there's a reason that we would see this. The confounder is what? High temperatures, right? High temperatures. When there's hot weather, people buy more ice cream. So there's more ice cream sales. And what else? There's more drownings. People go swimming. So this is just another iconic example to help you understand it's not that the ice cream is causing people to somehow get stomach cramps and die, so don't eat ice cream. No, it's clearly caused by something else, and these two are just associated. But then this is where we really have to do some hard work, where it looks like the relationship may be causal, but it's complicated and hard to tell. And that's what we talked about here. And a lot of what we're going to be doing in this class is looking here at this types of questions like health and wealth. You know, like we looked at before. We just said, does health cause wealth? Does wealth cause health? Is there something else, like learning statistics, that causes both of them? Or a mixture of all three with a complicated causal pathway pattern? Or a mixture of all three. Okay? And that is really, this is a cutting edge of statistical research, concerns itself with how to tease out those causal patterns. And then the clear causation, well, how do you arrive at clear causation? Well, there's experimental data that, smoking nicotine is a clear carcinogen. We've done many studies on other mammals that show that in the laboratory how that happens, and there's a huge amount of evidence, both observational and experimental, to show that. But he's right that it was controversial at first, and in fact, when I first started teaching statistics in '84, from the book that I modeled these notes on, the book said no, they still didn't think that it was clear causation, although I thought it was, so I didn't teach it that way. But that's pretty clear now. Okay? So now let's look at, so now these last two pages are just going to be basic review of the regression line. A lot of it's just going to be algebra 1, how do you get the equation for a line, etc. But there's something a little bit different about the way that I've taught it in Stat 100 and teach it here that I think is helpful that you should look at. Okay, so the regression line. All right, so there's a scatter plot, and here we have the x, and here we have y. All right, and these are, I just drew the outline of the scatter plot here. It's a series of dots all through here, You can imagine lots of little dots. Okay, so, and when the scatter plot shows a roughly linear trend like that, roughly linear trend, then a straight line here's the regression line. The regression line, a straight line, this right here, this line. A straight line can be fitted through the data to describe that trend, this linear trend. You see a linear trend with the points here, a linear trend, it slopes up like this, and it's not a curvilinear trend, but one that looks like this, follows sort of an elliptical shape here. And then a line, the regression line, can be used to estimate the mean value of y at each value of x. You can see that for values of x here, there's going to be a big scatter, and this regression line, in any vertical strip, there's going to be a scatter of points, and this regression line estimates the mean value within that vertical strip. Now, it's also called the least squares line because it's the line that minimizes the sum of the squared residuals. Those are these distances off the line that minimizes the squared residuals of vertical distances the actual y's are from their predicted y's. It's the best fitting line in that sense. All right. Now, there's another line, though, and this line is one that if you didn't take Stat 100, you might never have heard of, and that's called the SD line. All right. That's the SD line. What is that? That is the line where if you translated all your x values into z-scores, into standard units, and all your y values into standard units, that would be the line where if there was a perfect correlation, all the points would fall. In other words, on this line, it's the line where ones of equal standard deviations equals z-scores. So when r is equal to 1, perfect correlation, all points lie on the SD line, and there's no scatter. All right? And this regression line is always less steep. It's always flatter, less steep than the SD line. And how much it's less steep is by this factor of r, the correlation coefficient. For example, the correlation coefficient measures the association between the two variables, right? So if there's a perfect correlation, then first of all, the two variables are in different units maybe, right? They certainly could have different averages and different standard deviations. This is the point of averages where the two lines cross. So let's say this was data on height in this class. Let's say we asked that question, height predicting weight. All right? Then height we measured in inches, and height is in pounds. So we need a common measuring stick to get the correlation coefficient. The correlation coefficient is unit free. And so we would change both of these. We'd normalize both of these to change them to standard units or z-scores, right? And then a perfect correlation means that you have the same z-score for everybody in here has the same exact z-score for both variables. So if you were average in one, you'd be average in the other. You'd be right there. If you were one standard deviation above average in height, you'd be a full standard deviation above average in weight. If you were 2 standard deviations above average in height, you'd be 2 in weight. And same if you were 1 standard deviation below average in height, if you were shorter, then you'd be exactly 1 below. Every single person, if there was a perfect correlation, would fall on this line of equal standard units. And that's the only way we can measure it. We can't say you're exactly the same height and weight. What does that even mean? It means you have the same exact z-scores, the same in standard units, in a common measuring stick. And what this regression line does is, of course, it's not a perfect correlation, and this says, okay, basically the slope of the regression line, let's look at it, is r times the standard deviation of y over the standard deviation of x. So people who are our best prediction for people who are here at the average, they cross, they're the same. But let's say you're one standard deviation above average in height. Our best prediction for you is not that you'd be a full standard deviation above average in weight, but that you would just be somewhat above average if there's a positive correlation, and that somewhat is r. So if r is 0.9, you'd be very close to you have perfect correlation. If r is 0, that would mean that knowing, like if this was height and this was GPA, you're going to have random scatter. You're just going to have random scatter. No matter what your height is, how am I going to predict any better your GPA? So I would just predict the average for everyone, and r would be 0. So we'd have a 0 slope. And so regression is, so in this case, we could estimate r by looking at, this is going to be, by looking at this whole distance here, and what fraction of it. This would be your estimate of r. It looks like about 0.6. Do you see? Does that make sense? About 60%. If r was 0, and here's r is 1, our regression line, if this was our regression line, r would be about 0.6 in this case. Does that make sense? Because do you see what I'm doing? What I'm saying is, if I divided up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just said it would hit about 0.6 or 0.5. Does that make sense? That's the way, an intuitive way to look at regression. It's very helpful. Okay, and of course, if you have a negative, it would just be the same thing. You'd have the standard deviation line going that way, and you would have, again, our regression line would be flatter. It's some mixture between a perfect, like right here is r is equal to 0. Right here, this is r equals 1. And a regression line is the higher your correlation, the closer your slope is to 1. Does that make sense? Not if it makes sense. Not if it does. I mean, go like this if it doesn't. Oh, good. Nobody's shaking their head that way. Great. Okay, so you all know this. This is very important, and it makes a lot of sense that the slope, if the standard deviations are equal, like when you're in z-scores, then your slope just is r. But if they're not, it's rise r times the standard deviation of y over the standard deviation of x, rise over run. Okay, so that's the basics, and we're just going to jump to an example in just a minute. We just have to look at one other thing, and we've had this in Stat 100, maybe other people haven't. The typical error around the regression line is called the standard deviation of the errors, and it's given by this formula, the square root of 1 minus r squared times the standard deviation of y. Now, it's known another way, this is also called the root mean square error. It features a lot in analysis of variance. This mean square error and the root mean square error, and this is what it is, and so does r squared. Those are going to come up over and over and over again in regression analysis. So I'm just introducing it to you here. And r is the correlation coefficient, and if you square it, we'll say it's the proportion of the variation of the y's explained by the regression line, r squared. And 1 minus r squared is the proportion of the variation of the y's that's left in the noise, in the error. Okay? So just so you can get a feel for this, we're going to look at this relation a lot, especially as we go to analysis of variance and regression analysis. But right now, I just want you to understand it intuitively. Okay? So just look at this formula, and let's think about it at the extremes. So when r is equal to plus or minus 1, what happens? 1 minus 1, 0. So you have no, here's when r is plus 1. It's going to be, you have a perfect correlation. And when r is, and you have no scatter around your regression line. So it's 0. The standard deviation of your errors, if you put a 1 or a negative 1 in here, is equal to 0, correct? So we can just do the same with the negative 1. It would be the same. All right. Now, how about when, let's go to the other extreme, when r equals 0. Let's look at that relationship. So now you put a 0 in here, and you get the standard deviation of the errors. The standard deviation of the errors is equal to what? You put a 0 in there. It's equal to the standard deviation of y. And that makes sense. We just talked about that. When r is 0, that means you just have random scatter, no correlation. And your best prediction, your regression line, would just be the average of the y's. And your spread around there, the spread is your standard deviation of errors, and wouldn't it be exactly the same thing? The standard deviation of that would be the same definition of the standard deviation of y. It's the typical deviation from the average. So it's the same. So that works out. Now let's just, in the last 7 minutes, let's do this example. And so this is an example predicting from exam scores. We're predicting final exam scores. Okay, and we have these 5 summary statistics. Here's our correlation, and here's our standard. So right here is our point of averages. And we can read right off here, that's the point 83 for the x's, and it looks like about 83. And for the y's, it's 73.6. This right here is our SD line, and this right here is our regression line. All right, now we want to find the equation for this line, right? The equation for a line is going to be some slope plus an intercept, right? So here's your slope, and here's your y-intercept. Now, find the slope. We just talked about what the slope is. The slope is equal to r times the standard deviation of y divided by the standard deviation of x. So r is equal to 0.6, and now it's the ratio of 2 standard deviations. Which is y and which is x? Well, y is always what you're trying to predict. So that's y and that's x. So y over x, rise over run. So when you look here, y over x, the standard deviation of y is 10.3, and the standard deviation of x is 9.2. So this is 0.67. Does that make sense? Well, let's just look and make sure it does. Remember what we do here. Draw this line straight through here. And does it look like this portion right here, you go over a certain amount, and how far do you go up? Does it look like that is about 2/3 of the way up to the top? Does it? Do you see what I'm doing? You can draw any right triangle you want. You can do it at 1 standard deviation, 2, they're all similar. So if you go over 1 standard deviation in the x direction, wherever that is, you want to go 2/3 of the way up. That agrees with that. That looks about right. That is 2/3 of the way up. Doesn't it look right? Okay. Now to find the y-intercept. Well, okay, we have this equation. Let's put the equation in. So far, what did we get? The slope. Now we want to get this. All right, so we're looking at this line. Now, this equation has to be true of every single point on this line. So it has to be, the only point we know is the point of averages, so it has to be true of that. So if we plug in the point of averages, the average for the final and the average for the exams, the average for the final is 73.6, plug that in, 83, then we can solve for the y-intercept. So let's do that. So we'll plug in point of averages. And what do we get? We get 73.6 is equal to 0.67 times 83 plus the y-intercept. And when I did that, I got the y-intercept is equal to 17.99. I'll round to 18, and I'll put that. Now I have my regression equation. All right, now use that regression equation to predict the final exam score of a student with an exam average of 90. So what we're doing here is we're looking at this little strip of 90 right here, and we're trying to get that right there. Now there's a spread, but that is our best prediction. So it looks like it's going to be about a little bit less than 80. So this is the point we're trying to get. We're saying for 90, what do we have there? We'll use this equation here. We'll use this equation, and we'll say y, our final, is equal to 0.67 times 90 plus 18. And when I did that, I got 78.3. So that looks about right. Yeah. Okay? Does that make sense? All right. Now, the last thing that we want to do is, do you think this prediction will be exactly correct? No. There's scatter. Look at that. So what we want to do is, give me a measure of that scatter. What's the standard deviation of that scatter? This is a point estimate. We want to give it a range. All right? We're going to give it a confidence interval later, but for now, let's just think of a range. So do you think that prediction will be exactly correct? No. We need to add some wiggle room to that prediction, so we use the standard deviation of the errors to do that. Later, we're going to build confidence intervals. What is the standard deviation of the errors for predicting the final score? So we're just going to use our formula, and that is the square root of 1 minus r squared times the standard deviation of y. So in this case, it's square 1 minus 0.6 squared. Now, y is the final score, what we're trying to predict, so it's times 10.3. And I got 8.24. Okay? So that means, now attach that wiggle room to the estimate. This is our point estimate. We want to give it a range, so we'll say plus or minus that. That's sort of just the way we're going to do this for now. And then we're just going to add and subtract that. So we get 78.3 minus 8.24 is 70.06, and 78.3 plus 8.24 is equal to 86.54. So we can write that as an interval here, and the interval would be 70.06. You put the lower number first and the higher number next. Okay, so your homework's just like this. So you should be able to do that now. It's just pretty much a review. And that's due, it's just one page, just very similar to this, and it's due Wednesday night. It shouldn't take you more than like 20 minutes.
Excuse me. Can we have the exact number of SDX and SDY?
Okay, here, somebody just asked me a question, which is X and which is Y? Y is what you're trying to predict. So the final is Y, and this is X. So there's your SDs. Does that help?
No, I mean, how can I get the number of SDY and SDX?
Right here, there's 10.3, and that's SDY, and that's SDX.
Thank
Okay?
you. Hi,
Okay, I'm going to stop this right now.
okay.
So.